Hi there, Luke McKinney, Prep 101's Physics 101 instructor here. In this video we look at rotational kinematics, otherwise known as the circular equations of motion, aka the equations of motion again, for more marks.
Rotational kinematics, well, things moving round and round. Now we've already looked at linear kinematics, and that's handy enough. We know if something is here, and it's moving with a velocity and has a certain acceleration, we can talk about where it is. And so if it goes over here, it's like, okay, it moved 10 meters that way. It's moving at another speed of 5 meters per second. It has an acceleration of 2 meters per second squared. And we can follow it around all over the place. And technically, we could do that for things going around in circles as well. Like, let's say, if I had a big circle bolted down in the middle, and I had a point A rotating around. So the whole thing's rotating around. So I know A is moving that way right now. Remember, the velocity at any time is a straight line, a vector. And I can talk about that in meters per second. I could say it's gone a certain distance, all of that. But what if I have another point here, B, in line with that? I could say, well, hang on, it must be moving faster to go the same amount. But as the wheel rotates round and round, I can see, well, hang on, A and B, they might be moving different linear distances and with different linear speeds, but they've clearly sort of moved the same amount around the circle. So it makes much more sense to talk about that instead. So what I do instead is I talk about the angle they've moved. And once I'm starting to talk about angle instead of linear distance, then I talk about angular velocity. That curly W, it's the Greek letter omega, but just call it angular velocity because that's what it is. And now, instead of having to work out all the separate linear speeds of A and B and any other point, now I know every point on this wheel, no matter what point I'm looking at, is all moving with the same angular velocity, which is measured in radians per second. Now, what did I just say there? What's a radian? A radian is a unit of angle. You might have seen before that a circle has 360 degrees in it. And that unit is useful for some things. It also has 2 pi radians. And this unit is more useful for other things. So if I have a circle, if I go around the complete circle, that's 2 pi radians. If I only go around half a circle, that's half of that, so that's pi radians. If I only go a quarter of a circle, that's a quarter of 2 pi, which is pi over 2 radians. Don't worry, you don't have to memorize these or anything, but you'll see them several times and it gets easier to remember. And you can always convert. We remember there are 360 degrees and 2 pi radians in a circle. So to convert, you can use your calculator or you can go degrees multiplied by 2 pi over 360. And if you want, that even simplifies down to pi over 180. Now, why would we bother learning a new unit if we already know degrees? Well, because these radians do something very useful. The idea is, if we have a point A and it rotates a certain angle in radians, well, now I can find the linear distance moved is just the radius of A times that angle. And I know A is moving at a velocity. The linear velocity is just the radius times the angular velocity. And the linear acceleration is just the radius times the angular acceleration. And we remember, oh, we talked about this before, this acceleration is tangential. So that's the tangential acceleration. We remember if we're going around in a circle, we're always going to have another acceleration towards the center of the circle, the centripetal acceleration. And we just make sure to give them each their own names each time, and we won't get confused or upset about that. So now we have the linear position, that's displacement, velocity, and acceleration. And now we also have the angle, the angular velocity, and the angular acceleration. And those will obey the same rules. Now, if we have rotational kinematics, then we have rotational equations of motion. Just like for the linear, we had linear equations of motion with the same condition going ahead. Now, always say the condition at the start. That's how you know which type of problem it is. These are for constant acceleration. We saw this back in the first equations of motion. If it's constant acceleration, it's equations of motion. If it's not constant acceleration, it's some other type of problem, usually conservation of energy. Now, back in linear, we had new velocity is old velocity plus acceleration times time. So now we have new angular velocity is old angular velocity plus angular acceleration times time. So you see, we're basically getting double marks for writing the same equation again with curlier letters. New position minus old position, so change in position is old velocity times time plus a half the acceleration times time squared. So the angular version is the change in angle is equal to old angular velocity times time plus a half the angular acceleration times time squared. And remember, any of these numbers might be negative. You just plug that into the acceleration, into the equation. And you see here, new angle minus old angle. So that means angle covered. How much angle did it rotate through while we were doing all this? And then the final, the new velocity squared minus the old velocity squared is equal to twice the acceleration times the change in position. So likewise, new angular velocity squared minus old angular velocity squared is twice the angular acceleration times the change in angle. Beg your pardon, that omega got a little flattened out there. And a C, same as first time, this one's notable because it doesn't have any time in it. So if you're asked how many rotations does a record player make in 2 minutes, you'd use the ones with time. But if you're told a wheel grinds to a halt after 30 rotations, then you'd do the one with no time in it. Now notice there, we said rotations or revolutions, and that's not actually a unit of angle that we've been using. So we have to watch how to do that. And what we remember is that one rotation or revolution is a full circle. So that's 2 pi radians. So for example, if we say something does 2 revolutions, that means the change in angle is 2 revolutions. So that's 2 times 2 pi is 4 pi radians. One thing that occasionally comes up is the revolution per minute, or PM. And you just convert that at the start of the problem. So 1 revolution per minute, 1 revolution per minute. So that's 2 pi radians over 60 seconds. So that's pi over 30 radians per second. And now that's angular velocity in a unit we can use. And again, other parts of the problem, any equations of motion problem, once you've got constant acceleration, you'll be given some numbers directly and other numbers are sort of implied by the words. For example, if something comes to a stop, then the new angular velocity is 0. Whereas if something was at rest before it started moving, that just means the old angular velocity was 0. But overall, you'd practice these almost at the same time as the linear equations of motion, because it's double marks for doing the same sort of problem all over again.
I hope that was useful. There's plenty more useful videos in the playlist and even more useful exam style practice and tips and all sorts of things in the prep sessions. So make sure you join the Prep 101 Facebook Study Hub. You'll find out about everything we're doing there when the prep sessions are on, and there's even sometimes free ones, so you don't want to miss those. Hope I'll see you there.